All right, so we're ready for the last talk of the day. Uh, Alfigen, Sebandal should be speaking about the Talented Monoid view on Lie bracket algebras arising from Leavitt Path algebras.
Thank you. Thank you for this opportunity to be able to talk to here, and I appreciate it a lot. Um, so the title of my talk today, as you can see, is a talented monoid view on Lie bracket algebra arising from Leavitt path algebra. So um, I came to the decision to change a little bit, but this is what you can see in the website. But essentially, my talk will be around talented monoid, Leavitt path algebra, and a little bit of Lie bracket algebra. So it's not that one, but similar to that one. Okay. So my goal for today is for us to have this um, feeling of what we can do between or among these three concepts: talented monoid, Leavitt path algebra, and Lie bracket. So essentially, what I want or what I hope is that at the end of this talk, we will be inspired, hopefully not terrified, but inspired of what is the future there is in terms of the world of algebra in these three concepts, I hope. So this talk will focus on three papers with my colleagues. Oh, sorry. Okay. With my colleagues from Philippines, Jocelyn Villela from Mindanao State University, Ruzbe Hazrat, who we all know so much, from Western City University, and Wolfgang Bock of Technical University of Kaiserslautern in Germany. So these three papers are just recently published. So two of it are published already, and one is in as a preprint. So if you are um, uh, interested, then you can get them. So we have seen so far that given a graph, we have a Leavitt path algebra, and we also have a glimpse of the talented monoid, but not so much, but we already heard that word talented monoid so much in this entire 2 weeks, right? So now the question probably is, how can we relate these two guys from point of view of the graph, which is practically geometric Leavitt path algebra, so the algebraic structure there, and the talented monoid, which is a monoid, so the monoid structure there. And now we try to insert this thing here, the Lie bracket algebra, which is already related to Leavitt path algebra. So I will try to connect that to the talented monoid as well. So first, what is a gamma monoid? So a gamma monoid is actually basically a monoid with a gamma acting on it, with a group gamma acting on it by homomorphism. And this is a pretty simple example of a gamma monoid where gamma is equal to the set of integers and our monoid is this one. So this one is actually a Z monoid. Now let's um, meet the term called gamma order ideal. So it's basically a gamma monoid. M, a subset of, a gamma monoid M is a subset I of, okay, let's erase that. A gamma order ideal is a gamma submonoid I satisfying this thing here. And essentially, we will be focusing on this thing, most specifically Z order ideals where our gamma will be equal to Z. So we need this thing here in the entire talk, but we don't need to remember this. Just keep in mind that we are working on them. So I will present some results found in gamma order ideals that are very familiar with us in group theory or modules. This first thing here is, I think, the third isomorphism theorem, if I am not mistaken. So basically, the third iso also holds for gamma monoids. And this funny funny isomorphism here. So why did I put that there in this presentation is because of the word refinement. We need refinement to be an additional condition for our gamma monoid because of we were adding gamma order ideals here. So why why we need um, refinement then? That will be answered in the next slide. But what is refinement? Refinement is this definition here. So essentially, any sum can be refined. That's just what we need to remember. Now, this is let T be equal to this set, and where addition or plus is using this table here. It could be verified that this is actually a monoid. And if we let gamma be equal to the trivial set or the trivial group, then it's easy to see that it becomes a gamma monoid. And then, if we take a look at 1 plus 1, which is equal to x plus x using this table, we cannot refine it anymore. So this is not a refinement monoid. We take a look at these two gamma order ideals, A and B. Now, B plus B is an element of A plus B. However, B is not an element of A plus B if we check it. So that is the problem there. We found a summand which is not found in the entire set, which basically disagrees with our definition of a gamma order ideal. So in this case, A plus B is not a gamma order ideal. So we found an example of a non-refinement gamma monoid where it has order ideals which are not with whose sum is not an order ideal basically. Hence, we need this thing refinement here. And if we take a look at the proof actually of this theorem, we really need it. Now, we define three types of order ideals. First is the cyclic, comparable, and non-comparable. We define these three order ideals using this pre-ordering here. So x is greater than equal to y if x could be written in this form. So basically, this type is focusing on how we can compare their elements, essentially. So as an example, if T is equal to this thing, it is a free abelian monoid with the action Z on T defined in this way. So essentially we're just kind of shifting the arrangement of this quadruple. And we can see that 4x is equal to x, which is very easy to see. So it is a cyclic Z monoid. So now we are going to define terms that are very familiar with us actually in group theory. So these are composition series and many other things. So we have here a gamma series. It is this series where each of this thing here are gamma order ideals. And we say that it is a composition series if each of the quotients are simple gamma monoids. Now we put something new to that definition, I think. So we say that the gamma composition series is cyclic if all the simple quotients are cyclic, and same with comparable and non-comparable. So very easy to remember. And now it is also possible that the simple quotients are not of the same type. So we put name with that again, and we call it a mixed type. Now this is the famous Jordan-Hilder theorem. So thank God, Jordan-Hilder theorem also holds for gamma monoids, which basically tells us that every gamma series could be refined, and this composition series, they are equivalent to any other composition series we can find for a gamma monoid. So this is the definition of a directed graph, which we have seen in this past week, so it's okay. And now, just a recall, in this graph, this thing here, U, is called a source since no edge goes to U. This thing is called a sink because there's no edge coming out of U. V, sorry. This is an isolated vertex, and this is a loop. So now we define two things that relates or that tells us something about the set of vertices, and these are hereditary and saturated. So what is hereditary? It basically tells us this here. If H is a hereditary set, if U or the source vertex is in H, then we are forced that the range vertex is also in H. So it inherits this property in some sense. And saturated, if all of the ranges are inside the set, then we are forced, if it is hereditary saturated, that the source of those vertices or edges are also in H. So as an example, if we take a look at this graph here, BC. So if we take a look at this thing here, we can see that A is connected to B, or yeah, let's just say it is connected to B. However, we cannot use saturatedness to invoke that A is inside the set, this set, if we want it to be hereditary saturated, since we have A is connected to E and D, but they are both not inside the set. And same with D. However, this set, the set containing C, if we take a look at it, okay, this one. As you can see, B is connected to C, and it does not emit any other vertex. So the range set that is coming from B is essentially just C. So if we invoke saturatedness, it should be inside. So this is not a saturated set. So the definition of a Leavitt Path algebra. Okay, now this is the Gelfand-Kirillov dimension. So it looks kind of messy. It looks messy to me, but we don't need really actually to really understand this thing here, which we will find later on why we don't need this thing here. So let's just forget that. But but if you want to know, this is the formula for the Gelfand-Kirillov dimension. If you just want to know, but we don't need that information. So graph monoid, I believe Rusbe has already introduced this term or this thing here earlier, the graph monoid M sub E. This is for a row finite graph. And now we define the talented monoid. So the talented monoid of a row finite graph E, denoted by T sub E, is an abelian monoid generated by this set here. So for every vertex, we have V of I, subject to this relation. So as you can see, it really looks like the graph monoid. We just add something to it, which is something of, we add some sort of indexing in some sense, and we just add one every time we do it. And okay, so that's the talented monoid. The additive group acts on the TE by automorphism by shifting indices you define in this way. And actually, we can extend this to every element. So it follows that TE is a Z monoid. So now for every vertex V, we simultaneously use a vertex as an element of the talented monoid and as a vertex of the Leavitt Path algebra. But in this, for instance, in this slide, V is defined, not defined, but for just convention, it will be equal to V of 0, and that will be 0V, using this equality here. So essentially, for any n, we have this V of n is equal to NV. And actually, the talented monoid is a refinement Z monoid. So that's good news, so that we can essentially use the Jordan-Hilder theorem and all of the other isomorphism theorems because it's a refinement Z monoid. So now, as an example, we take a look at this very simple cycle here. In ME, U is equal to V, and V, oh, sorry, this is wrong. V is equal to U. So this is wrong. So it should be V is equal to U. Now in TE, we can see that U of 0 is equal to V of 1. We just add 1 again, and that is equal to U of 2. So in the talented monoid, we have seen that U is equal to 2U. Now this looks familiar because actually it tells us about the comparability of elements, right? The three ideal types that we have, the cyclic, non-comparable, and comparable. Now, this equation here tells us that actually the ideal generated by this thing here is a cyclic ideal. Now, we can ta- um, take a look at this next example. The only difference is that this has an exit. So what happens if we have an exit? So U of 0 is equal to V of 1, which is equal to W of 2 plus U of 2. I hope it's correct. So essentially, we have U greater than 2U. So from equality, we get strict um, this thing here. So actually, this tells us that the ideal type that we get is a comparable one. And take note, if we have a cycle without an exit, we have equality, and if we have an exit, we have this inequality. So actually, we have a result stating that every cycle without an exit corresponds to cyclic ideals. So in this case, it is a cyclic ideal. So that will be information will be very handy later on in our discussion. So just backtrack what happened. First, we defined gamma monoid, and just we saw the definition of Leavitt Path algebra, ME, and then TE, which is a refinement Z monoid. So now, this is like a cute diagram of what we did. So from E to TE, and then E to Leavitt Path algebra. So the question is, what is the relationship between these two algebraic structures here, TE and the Leavitt Path algebra? So to answer that, one of the things that could answer or could be a tool in this relationship could be answered in this slide. If we have LE, the set of all hereditary saturated subsets of E, LTE, the Z-order ideals of TE, and this thing here, the graded ideals of LKE, if we define H to be, if we map H to the ideal generated of H, and at the same time, if we define, or if we map H to the gamma order ideal generated by H, this is actually a lattice isomorphism. So essentially, if we want to take a look at Z-order ideals, it is, I think, enough to take a look at hereditary saturated sets. As well as if we want to take a look at the graded ideals of the Leavitt Path algebra, to have a good visuals, we take a look at the hereditary saturated set as well. So this is for the row finite graph, if I have not mentioned it. So this thing here is very handy in the study of talented monoids. So the answer is that one of the tools we can use are hereditary saturated subsets. So now we define a chain of cycles. So this is a chain of cycles. So it's very understandable, I think. And this is for cycles that are disjoint. By disjoint, we mean that for any two cycles in the graph, they don't have any common vertex. If we let D1 be the maximum length of a chain of cycles, and D2 the maximum length of a chain of cycles with an exit. So for instance, let's just take a look at this thing here. D1 will be equal to N, and D2 will be equal to N minus 1. Because the cycle that or the chain that we'll be looking at is from here until the rest. So it is easy to see that D1 is greater than or equal to D2. So why do we need to know this? We need to know this because it actually tells us a nice result by Alamadi, Al-Salami, Hain, and Zalmanov about the Gelfand-Kirillov dimension of the Leavitt Path algebra. So the GK dimension is finite if and only if E is a graph with disjoint cycles. As a matter of fact, we can compute the Gelfand-Kirillov dimension, which is equal to this thing here. So that's why I said that we don't need to really immerse ourselves with the definition, because this thing here is what we need in this talk for us to um, understand the next stuff. And since D2 is less than or equal to D1, actually we can rewrite this thing here into this thing here. So as an example, in this graph, D1 is equal to 2, 1, 2, and D2 is equal to 1. So we only have this cycle. If we compute it, we can see that the Gelfand-Kirillov dimension is 1. And similarly, if we compute this one, I hope I computed it correctly, the GK dimension is equal to 4. So as you can see, just using the pure geometric view, we have found an algebraic point of view, which is the Gelfand-Kirillov dimension of the Leavitt Path algebra, which is very nice actually. So that is what our goal now. So as you can see in this part, in the geometric point of view, we have the chain of cycles, and in the algebraic point of view, we have the GK dimension. Now, since we have been talking about gamma series and gamma composition series, actually, what we can relate with a talented monoid is the Z composition series. So what we want is a length of a Z composition series that will hopefully correspond to D1 or D2, or in that direction, hopefully. So if E is a finite graph and LKE is associated Leavitt path algebra and T is talented monoid, then these are equivalent. First, E is a graph with disjoint cycles, so it tells about the geometry. Second, TE has a composition series of cyclic and non-comparable types. It tells us about the monoid structure of TE. And third, LKE has a finite GK dimension. So this theorem here is quite nice because it relates the three stuff that we want to connect with each other. So how can we do that actually? From a composition series to find D1 or D2, let's see what is the idea behind that. So for instance, we have this chain of cycles. We let this guys here, the vertices found in this thing here, be H1. The vertices of this guys here will be H2, and the entire thing will be H3. So we actually have a chain of hereditary saturated sets. So as Leah would say, let us convince ourselves that each of these are hereditary saturated sets. Now, if we remember that every hereditary saturated set corresponds to Z order ideals, so it implies that this sequence also corresponds to a sequence of Z order ideals, where each of these II is the Z order ideal generated by HI. Now, if we take a look at this quotient, actually, the thing we want to visualize about quotients is just, it's like we deduct the, let's just call it denominator. It's like we deduct the denominator from the numerator in some sense. So, for instance, if we take a look at I3 mod I2, I3 mod I. So I just changed this into i's just for visualization purposes. So I3 mod I2. So what we actually get is we subtract or we delete this entire thing. So what we get is this thing. So that's why it will correspond to this subgraph and so on. So as you can see, if we remember that every cyclic z-order ideal corresponds to cycles without exit, now since this guys here doesn't have an exit, so each of these quotients are actually cyclic z-order ideals. So we have found a series, a z series corresponding to this graph here, which is a cyclic uh, z composition series. And luckily, the length of this series is actually equal to the D1. Well, that is not always the case. For instance, this graph here has a sink, or for instance, C3 has an exit and a sink. We will not have the same result, same result. However, we also have, luckily, we have a computation of the Gelfand-Kirillov dimension using any kind of graph. But before that, we have this example. If we compute the GK dimension is equal to 3 and 4. However, if we take a look at the talented monoids, this thing here has a periodic element, which because 1W is equal to W. If we take a look at TF, so this graph here, we cannot find any periodic element. So these two talented monoids cannot be isomorphic. However, they have gamma composition series which are equivalent. So if we just take a look at this two series, we can find that their simple quotients are actually equal, or essentially they are equal. So before we go to the computation of the Gelfand-Kirillov dimension using composition series, we have this definition here, the upper cyclic series. It is a chain of gamma order ideals where where the quotient is, this quotient here is the largest cyclic ideal of T mod II, and we call I sub n the leading ideal of the entire thing, and which we denote we denote n by LCT. So we don't need really to really focus on that, but it's actually very important. But this thing here is important in computing the Gelfand-Kirillov dimension because of the next result we have. So for a finite graph with disjoint cycles, we let S be the largest non-comparable gamma order ideal of the entire talented monoid, and I the leading ideal of the upper cyclic series of TE. If we let D1 be equal to this number and D2 be equal to this number, then we have the computation of the Gelfand-Kirillov dimension. So as you can see, from a formula coming from a very geometric point of view, we have found a formula which we are looking at the monoid structure of the talented monoid. And as a corollary of that, it is good to know or good to take note that the Grothendieck group are isomorphic, then the Gelfand-Kirillov dimension are equal. Which is pretty nice in my opinion, because essentially the point or the main goal or the highest goal is to prove the classification conjecture. And so this actually somehow tells us that we are in the good track. So again, this is what we have now. Let's talk about Lie bracket. So From the Leavitt Path algebra, the Lie bracket of that algebra is already known, and our goal is to connect the Lie bracket to the talented monoid as well. So if this is the definition of a Lie algebra, so it is a k-vector space together with this mapping where it is bilinear. We have this thing, I think it is called anti-commutative or something, I forgot. And third, we have the Jacobi identity. So given an associative K-algebra, we have a natural Lie algebra associated to this K-algebra using this definition of the Lie bracket. So basically, if the Leavitt path algebra is an algebra, then we can obtain its corresponding Lie algebra. So the following result about Lie solvable and Lie nilpotent will come from an article by, if I hope I'm not mistaken, by Abrams and Mission, I think. So the following results will be an adaptation of the talented monoid point of view of that article. So we define these guys here, L to be L0, L0, and Ln with a parenthesis to be equal to this one and Ln. So it's pretty much the same as what we have known in the definition of nilpotency and solvability in our old group theory, I think. Then L is solvable if we can find an n such that this is 0 and similar with nilpotent. The associative algebra A is called Lie solvable of index n if its associated Lie algebra is solvable of index n, and similar with Lie nilpotency. So this is a result involving Lie solvability of the Leavitt path algebra. So if the Leavitt path algebra is Lie solvable, then first, the talented monoid has a composition series of cyclic and comparable types. And second, the Gelfand-Kirillov dimension is less than or equal to 1. And the next result is a characterization of Lie solvability with two cases. The first case is that the characteristic of the field is equal to 2. So LKE is Lie solvable if and only if the Gelfand-Kirillov dimension is less than or equal to 1. And one of the following hold for every vertex V. We have either the ideal generated by V is a minimal non-comparable ideal. Second, it is a cyclic ideal with this thing here. Or third, for every edge emitted by V, these guys are non-comparable as elements of ME. However, we can also view this thing here as elements of talented monoid just for easier view. It's actually okay if we view them as the graph monoid. And then for characteristic that equal to 2, the Leavitt path algebra is Lie solvable if and only if the Gelfand-Kirillov dimension is less than or equal to 1. And for every vertex, we have this one. And for Lie nilpotency, the Leavitt path algebra is Lie nilpotent if we have this one. So essentially, it is the same with the Lie solvability for characteristic not equal to 2. So we can directly say that Lie solvability and Lie nilpotency are equivalent in the case of characteristic not equal to 2. So that's it for nilpotency and Lie solvability. Now we go to simplicity. So first, we define a balloon of a graph. So this is the definition of a balloon. But, okay, this guy's here. But just to easily see it, we have this visualization. So we have a vertex V and a set of vertices W. We say that V is a balloon over this set W if there is a loop, and then V is connected V is connected to the elements of W, and it is not connected to any other vertices outside W. And also, there is no edge coming from outside W, or no, sorry, outside, not equal to V. So as you can see, there's no edge going to V, aside from the loop, of course. So that is the definition of a balloon. Now, this is essential because Lie simplicity actually revolves in this in this definition of a balloon. Now, this is a characterization of a balloon in terms of the talented monoid. So a vertex V is a balloon over W if and only if first, this guy here is a maximal Z-order ideal of TE which does not contain V. So if you can see, it essentially tells us that the entire thing without V is a hereditary saturated subset. Second, we have this one. And third, the talented monoid of the quotient graph over H is simple cyclic. So this is a characterization of a balloon. Let's call that theorem heart, just for fun. So we have here a characterization of Lie simplicity with the assumption that the Leavitt path algebra is not simple. So this guy here is simple if and only if for every vertex V not in some Z order ideal I. Theorem, this thing here. So 1, 2, 3 are satisfied, and we have this summation inside this Lie bracket, where W here is actually the set of vertices in the minimal non-cyclic Z-order ideal of TE. Yeah. This one here, as a Leavitt path algebra, not simple. This thing, yeah. No, yeah. As a Lie algebra, that will correspond to this phrase, I think. Yeah. So as actually, if we can, it basically tells us that for every vertex outside the or outside the minimal Z order ideal of TE, it is a balloon. So that is essentially the idea behind this theorem. And this, the last theorem, I think, is quite nice because it gives us an simplicity, graded simplicity and simplicity of the Leavitt path algebra in terms of the Lie brackets. So the following are equivalent. First, the Lie algebra associated to LKE is simple, and LKE is graded simple. By saying that it is graded simple, essentially says that it doesn't have any proper graded ideal. And LKE is simple, and we have this summation, or the identity of LKE is not inside the Lie bracket. And I think that's it. Thank you for your attention. I am not sure if which is not zero. Yeah. That's right. That's right. If we assume that it's simple, then we're done. Right.